Okay, let me see, where is my, I have audio here. 1, 2, 3, 4, 5. Yes, I do. Okay, so um, we're going to talk about pointers today and kind of cover all the pointers and smart pointers and raw pointers, going through them quickly. Kind of a review of all the pointers since we've learned from IPC 144, and then moving to smart pointers and understand how they work. Um, uh, so first, I will start with a regular syntax of a pointer, and let me bring this up. Bring the lectures note up so to see what I'm talking about in proper order. And there we go. So uh, quickly going through what we know about pointers. We know pointers are to store memory locations. So they're essentially variables to hold addresses. They allow indirect access to data, which essentially means I can access the data via the object itself if it wasn't dynamic, and through pointers I can indirectly access to them in other scopes, so I can pass the address of stuff around and use pointers to access them. Pointers are crucial to algorithms, returning dynamic sizing or efficient iteration. Um, we process variable length without copying. We use pointers for anything that either dynamically or remotely works with other variables. So a pointer by definition is defined by adding an asterisk to the beginning of, I know it's IPC 144, but I have to go quickly through everything. So a pointer essentially gets created by adding an asterisk after the data type, and that together with the data type, that means pointer. Essentially, PTR is a pointer to a type integer. With ampersand, I can extract the actual address of an integer, and therefore indirectly I can use the pointer to manipulate, read, write, do whatever I want to do to the original value. That's what pointers are. You good? Okay. So that's the original thing, and this is pointer basic. I'm very quickly going through all these things, so stop me whenever you think it's needed. Okay. Talking about pointer arithmetic, what is pointer arithmetic? So essentially, we can actually do arithmetic with the pointers themselves. So looking at the start pointer that I have over here, I have numbers 10, 20, 30, 40 in an array. The size of my array is 5. And start is a pointer that points to the beginning of the numbers. By definition, the name of any array actually points to holds the address of the beginning of the array. Okay. So now I can actually iterate through the elements of the array using pointer arithmetic instead of indexes, which means essentially I can say I'm going to add an integer to the pointer, and when adding uh, a, the value of 1 to a pointer, essentially the size of the target will be added to the address. Therefore, let me actually bring a better code than this. There we go. So when you add 1 to a pointer, the pointer points to whatever object it is. That size will be added to it, and therefore I can iterate through it. So when I say target of start plus I, it's not 1 that is being added to the address, but it's size of the integer at line 7 that is being added to the pointer, and therefore I can access the elements one by one. That essentially translates in C language to start I. So when you say start I, that's essentially line 11. It gets translated to target of start plus I. And because of this fact, arrays start from 0. Because when you add 0 to the beginning of an array, that means the first time. Okay? So essentially, when I walk through this, uh-oh, okay. I'm sorry, this Windows 11 is a little nuts when it's Windows management thingy. There we go. Okay, so now if I go through this step by step, obviously start points to the beginning of us. As you see, it says 48 over here. If you look at the numbers shows 48 too. So they're both pointers. And now when I do like this, some will be added. So essentially start I will be added one by one to it. And I can actually add the values. Now, if I look at what the arrays are, essentially each array element has the value 10, as you see, and the address that is sitting at its start plus I. So I'm showing where it is located. And if you look at the hexadecimal values as I kind of traverse through the array, you will see that the numbers are added by 4 one by one. To kind of illustrate that better, I made that long. I converted that integer address that is hexadecimal to a regular integer. Essentially, that's the address. And it's C72 is at the end. And then it becomes 76. And 80, as you see, 4 is added to it as it goes forward. Another way of doing pointer arithmetic is adding to the value of the pointer itself. When I say integer pointer numbers, PTR is pointing to the beginning of the numbers first, but instead of having start plus I like that, I can actually say target of PTR by itself and add to the value of PTR. The difference is that the PTR does not point to the beginning of the pointer anymore, and it actually points into the individual numbers. It kind of works like an iterator now, which means the pointer points to individual elements and goes forward. Again, these are raw pointers, nothing to do with C++. And it works the exact same way. And as you see, the sum will be the same with no difference. So this is pointer arithmetic. What happened? What did, okay, sorry. Okay. I don't want to do anything. How do I get out of here? Okay. What the heck? Well, how can I get it? Okay, let me take this away. Hopefully I can take it away somehow. Windows. Okay, how do I get rid of this? Sorry about that. I no idea how to get rid of the damn thing. Okay, I don't know. I guess we are stuck with it. Okay, toolbar down there. Let me see if I can. Let me see if there's anything in here that I can.
Please confuse close the window. Go down. The items, please. Yeah.
Here, this is the one.
Yeah, and solid and there. Sharing. That one.
This one?
No, the one. Like the right.
This
Yeah,
one?
and this closing.
Thank you. Now you can understand what is the meaning of proper system analysis and design. Okay, they create something that somebody who's worked for computers for 26 years cannot find out how to close it. Thank you. Okay. Anyways, I hope Microsoft sees that. All right. We used to have Big Blue Button. It was a beautiful thing that you could teach with it, and it was an amazing thing, but yeah, cuts, and we don't have it anymore. Anyway, so let's get out of here. This was the pointer arithmetic. Okay, and now, what the heck? Again? Why it keeps going? Okay, let me go over there. Let's see if I can do the same thing again. I do not want this. I do not want this. Please, I do not want this. Okay. All right. All right. Seriously, I'm not doing it. It's coming up by itself. All right. So pointer arithmetic. Now, the next thing that we need to know about pointers is dynamic memory allocation. So essentially, pointers are used for dynamic memory allocation, which essentially you have a pointer and you point to a newly allocated memory, and you can go through the dynamically allocated memory exactly like a regular array, or you can use pointer arithmetic. It does not make any difference. It's exactly the same thing. The only thing that you need to, now it's just an example over there to see how the pointer arithmetic is working with this, but the only thing that we need to do is to always have to delete the value. This is the drag that we have for all the pointers in C or C++, where we do a dynamic memory allocation, we are responsible to wipe it out, and if we don't, we are in trouble. Okay, so that's that, which we're going to fix today, hopefully. Okay, so this is for dynamic pointers. Now, another syntax that we had with pointers was working with compound statements. So essentially, but with compound objects. So essentially, this is exact same code that we had over there, but the difference is that with the structure. So what I'm doing in here, I'm receiving number of courses, dynamically allocating the number of courses, and one by one, I'm receiving the number of courses and using the pointer as if I'm using an array. But if you want to access the internals of a compounded statement, we use the arrow operator to actually say the pointers that points to the structure go to the title inside and do something. So essentially that, after a pointer, essentially means pointer is now pointing to a structure or a class, and I want to go inside. And that's what's going on. If I wanted to use dot to do that, then I had to, for this, I had to do something like this. So the equivalent of that one is essentially saying target of PTR, which is a reference dot. to convert it to something like this, which is hideous. So instead of doing such a complicated thing, target of video.title, I can say PTR add, and it does the exact same thing. Okay? And obviously at the end, again, I have to delete all the stuff that the object is pointing to prevent dangling pointers and set it to null. And that's with pointer to a structure. Now, understanding pointers and two-dimensional arrays. Look at this for a second. By the way, this is how you create annotations. You click, it opens, and then you close. Anyway, so say this is a two-dimensional array that I have, and the two-dimensional array of mine has 3 arrays inside. So that's essentially 1, 2, and 3. And each array has 4 elements. Okay? If I have an array like this, I might want to show it like this. So essentially, this is the array A, and in here I have one, 2, 3, 4. Oh, that's 3, 4. And you get the message, right? In here I'm going to have 10. In here I'm going to have 20 and 30 and so on and so forth. I'm not going to go through the whole thing. So I have an array, a two-dimensional array. So essentially this one, for example, will be A1, 1, right? This will be A11 because this is 0. So essentially, the index of all these things will be like this. So this is index 0. This is index 1 and index 2. And again, this is for the individual arrays, 0, 1, 2, and 3. Therefore, so that's going to be element 1, 1. Are we okay with this? Two-dimensional array? All right. Now the two-dimensional array that we have over here looks fine, but really, what is a two-dimensional array? Take a look at this. If I write something like this, if I write something like this.
I have a question.
Yes.
First you write row or column?
Always row. So what I did now, we know that when I write an array, it's actually a pointer pointing to a piece of location. So essentially, this is A that is pointing to the beginning of the array. Something like that. But what I did, I created another array, another pointer, PTR, and I'm pointing to the same that A is pointing. So what is the difference between A and PTR in here? A is a pointer that points to packs of 4 integers, which means if I add 1 to A, 4 multiplied by 4 will be added to it, which is 16 bytes. Because so that's why when I say A0, it means the first row. When I say A1, it means the second row. When I say, so A1 becomes a regular pointer, which that's why when you say A10, that means 10. When you write A11, that means 20. When you write A12, that means, so A is a pointer, A0, A1, A2 are pointers too. The difference is that A points to a structure or a pack of 4 integers, where A0 points to 1 integer. So what I did, I played a trick. I say reinterpret cast the address of A into a pointer to 1 integer. Therefore, PTR0 and A00 will be the same. Didn't I just compile it? No. Will be the same. Okay, we good? Now, take a look at this. I'm going to copy this. I'm going to make this 3, and I'm going to make this one 3 too. And run it again. Now, obviously, it's going to point to 4, right? Because this is 0, 3, essentially means A0, 3, that is 4. And PTR3 means PTR0, 1, 2, 3, 4. 1, 2, 3, right? And goes to 4. Are we okay? We good? Now, I want to show you something. What happens if I say PTR4? 0 is 1, index 1, and index 3 is 4. So what is index 4? It goes after the first row. Will I get segmentation fault? Am I going out of the thing? So where it's going, what is it going to pick up? It's going to pick up 10. Take a look. What does that show? It shows that there is no two-dimensional array in C language. It's a one-dimensional array that is simulated to look like 2. How? By making the thing that I told you at the beginning, where A by itself is a pointer that if I add 1 to it, it's going to go 16 further and so on and so forth. Okay? And another proof for it would be that if I even do this, what's going to happen is it's going to actually show you 20. Right? Because it doesn't know, it's simulating it, right? And the same thing over here. If I actually, if I actually, you see there's a wiggly thing underneath. So the syntax check, not the syntax checker of IDE, it's giving you some message. Something weird is going on here. So if I put 1 over here, 1 and 5, now the address of beginning is 1, and I go 5 further, and obviously it's going to fall onto 200. Which is this one. Right? Now, this is the regular two-dimensional array, which, again, as I mentioned to you, A0 essentially points as a single integer, but A itself points at 4 integers. Therefore, if I say, so the pointer representation of this essentially is going to be something like this. If I say cout target of A plus 1, if I do something like that, the outcome is going to be an address, because that's essentially A1. But if I put a 0 in front of it, it's going to actually show the first element of the second array, which is 10. Or to kind of show you that, if I say, because this is a pointer, correct? This is a pointer, correct? What if I say target of that pointer? Then it becomes element 1, right? So if I say target of a plus 1, then that becomes 10 too. Right? We good? All right. And the final thing, that becomes right? Because I'm saying to the target of a plus 1, which is the address of the second row, add 2. It means 2 integers. 1, 2. Okay, so that's essentially, they call it pointer notation for an array. Okay, as simple as that. This is something that you need to know. The pointer notation for an array. And let me just clean that thing up later on. So essentially, just to show you what I mean, if I have a, 2, 3, 4, if I have something like this, essentially what you're going to have will be, first of all, it's got to just think about it that way. It is doesn't allow me to type an asterisk. Don't know what to do. Maybe if I do it here. How do you type an asterisk? Okay, let me do something else. Maybe if I do it like this, it will not bug me anymore. Yes, thank you. Okay, so if I can have a, 2, 3 plus 4. That's the representation of the top, right? Now, I'm going to replace that A2, 3 with its equivalent. So it's going to be target of A2 plus 3 plus 4. That's going to be that. And for the last one will be A plus 2, and then plus 3, and then plus 4. So that's a pointer representation of a 3-dimensional array. And it keeps going like that. Again, it's a recursive thing. If you think about it, what I just said, I assumed that A23 is a pointer, I wrote the representation for it. Then I assumed A2 is a pointer, I put the representation for it. Then I put A2 as a pointer, and I just replace it, and that's the result. And that's the pointer representation for an array, which you do not need to know. Just letting you know that it can expand as many as you want. Okay, so that's that. Next thing, What if I do something like this? Instead of having an array of 3, 3 by 2, I can do something like this. I can actually create an array of 3 integers, a 3 integer pointer. So that means I will have this. Let me actually bring them up to see the diff. Actually, this was the array that I have. Now, this is what I'm going to have. And each one is 1 pointer. Okay? Now, having something like this, each one of them is a separate pointer. What I can do is to actually dynamically allocate different length of arrays in there. That means the first one is 10 integers, the second one is 20 integers, and the third one is 30 integers. But the syntax for it remains like a regular two-dimensional array, which means when you are writing over here, you can actually write something like AR2, 3. That still means the third element of the second array. But the difference between this type of arrays is that the length of each array is not equal to the previous one. This is called RAG arrays, arrays that are done dynamically. So each one is different. Very bad thing to do unless you really keep track of what is the length of each, because the first one 10, if you go 11, it's not going to back over here. That's going to be segmentation fault. If I actually pass the length of this one, if I go AR10 and try to do something, it's going to crash. It's not like the other one that is a continuous piece of memory that is fake to be two-dimensional. This is really a two-dimensional array, and each array is individual thing somewhere in memory. The real look of a ragged array is not that, but it's something like this actually. The 10 integers are here, the 20 integers are here, and the 30 integers are here. And they have nothing to do with each other with respect of location in memory. When you finish the 10, if you go further, you're going to go to heap. It's not, these are not statically allocated. Okay? And to delete the values for these, to delete the values for these, you have to go through a loop one by one and and delete them. So essentially, it's going to be something like this. You know all these things. I'm just kind of a quick reviewing. So essentially, to delete all those values, I have to do something like this. Now that is statically allocated array of pointers and dynamic array of pointers one by one. What if I want to make this one dynamic too? If you want to have something like this, then the story becomes a bit different, which essentially means you will have a code like this. So I'm going to say I need a pointer, an array of integer pointers. Okay, so he points to 4 integer pointers. And now each integer pointer points to a different size of array. So not only the individual arrays are dynamic, but also the main pointer is dynamic too. And to delete those values, you have to make sure to not only wipe out all the individual arrays, but also the main one, because that's a pointer too. So that's why what we call a pointer to a pointer. Okay? All right? We good with ragged arrays? This is all C. And not the new int stuff like that, but the syntax of the pointers are all C language. It has nothing to do with C++. Dynamic memory allocation is C++. In C language, we use alloc and malloc and free and things like that. There's a different ballgame. Okay? So that one is pointer to pointer. Another demonstration of a pointer to pointer is a scenario like this. So if I have a code like this, oh, two mains. If I have a code like this, from earlier of today that I mentioned, we know that target of PTR in this case, because PTR is pointing to the same place that A is pointing, when I add 1, this actually points to 20, right? Now, my question is, what happens if I do this? If I write over here void advance integer pointer P, and I write over here target of P++. And then in here, I'm going to write advance, and in here I'm going to put PTR. If I print PTR again, what is going to be the output? So PTR now is pointing to 20. So when I pass PTR, then the contents of PTR will be passed to P. So P will point where PTR pointing, that is 20, right? Therefore, when I say target of P++, that 20 becomes 21. We're good? You're okay with that? So if I do this, it's going to print the previous one because I didn't change it. Give me a second. Control C. Sorry, I'm going to bring the old one back and put this in the other. Yeah, so as I was saying, if I print this one, we'll see that's actually make that one 20 and 21. Okay? Now, if I do something like this, pointer to a pointer, and next time I do the advance using address of PTR, now the story becomes different. For this one, PTR is now pointing to 20. And the address of PTR is passed to P. So P is pointing to PTR, not 20. When I do target of P++, PTR will be added by 1, therefore advancing to the next one. So this advance is named incorrectly. This advance is add 1. And the other one is advance actually. So advancing a pointer needs the address to be passed. The other class had a question, couldn't I just pass the reference? Yes, you could, but that's C++. I'm talking about C. In C, that's the case. So the address of a pointer should be passed to a pointer to be able to advance it. And that's what we are going to. Okay? We're good? All right. Let's take a break. Come back. We'll talk about smart pointers. Now we're going to jump to C++. This was the whole raw pointers that we had. That we went through, and yeah. So we come back, we're going to talk about unique pointers. I'm going to let's continue. And continue recording. Today I'm now it's telling me this use of this lab will not be recorded. Support for recording is coming soon. Okay, okay, now it's recording. Okay, good. All right. So let's start with understanding what smart pointers are. The main problem with pointers and dynamic memory allocation in C++ is that, and C, right, quite frankly, is when you actually have a pointer to pointing to a piece of dynamic memory, you have to come up with a mechanism to make sure you delete the memory when the use of memory is you're not using the memory. The problem with that is that you always miss it somehow, and that's why you have lots of memory leak in C++ programs. So they said, okay, when you are dealing with dynamic memory allocation, let's create what we call a smart pointer. Let's create something that I don't need to keep track of what the pointers do, but pointers will keep track of themselves. For that case, we need two major types of pointers, really. One, a pointer that points to a piece of dynamically allocated memory and uniquely pointing to that one, which means that piece of memory should not be pointed by anybody else. So I have a pointer pointing to an array, and I've got to make sure that only this pointer is pointing to an array, and I cannot copy it anywhere else, therefore causing several pointers point to a piece of memory and one of them delete the memory of the other one too. The problem we had with copy constructions and stuff. We had to overload copy constructions because if we didn't do that, then two objects would point to the same piece of memory. I don't want that. So to do that, I'm going to create a class, a template that can replace a pointer pointing to a dynamic piece of memory. How do I do that? I created a template, type name, and I'm going to call it type, okay, class. I'm going to call it UNPTR. So essentially, this class of mine is going to impersonate itself as a pointer pointing to a dynamic piece of memory, which is unique and prevents two pointers pointing to the same location, number one. Number two, it's going to take care of its memory by itself, so you don't have to delete it. So what do I need to do? The very first thing that I need to do is obviously to have a pointer, to encapsulate a pointer to fix the problem. And that's going to be my MPTR. So that's my pointer. When I create and instantiate this pointer, what do I need? When I instantiate this pointer, I need to receive an address, a dynamic address that could be null, which means that nothing was allocated, it's just null. But if it's not null, or for whatever it is, I am going to set that MPTR of mine to the value of the PTR that is coming in. So that essentially takes care of my creation. So when I actually create a pointer, that's what I am going to do. So let me bring up the usage for it. So say did I save this? No, I did not. So this is G PTR PTR2. So obviously, this is my, I always write a tester, right? So I have an employee that has lots of, it's a regular employee that I have over here, and the employee has a salary and it prints itself, and I overloaded the insertion operator so it can be printed. It's just a class to show things. Now, to create an employee pointer using my unique pointer template, this is what I'm doing. Let me maximize this so I can split the window, so we can see what we are doing in here. So essentially my template says, give me a type. So when I'm actually instantiating this template of unique pointer, I'm passing the employee, therefore type becomes an employee. Therefore, I'm going to have an employee pointer inside. And when the constructor is happening, the address of the employee, which is a new employee, is for dynamic memory allocation, right? Or I could write equal to, same thing, right? I could literally write over here, he is equal to something like that. Same thing, right? So essentially, assignment of number of creation is a auto constructor. So it passed the address of a new employee to P. Therefore, P sets the MPTR to point that allocated member. Are we good? Simple, right? All right. Next thing I need to do over here in this unique pointer is to make sure no one else is going to point to that pointer. Okay? For that, it means I gotta make sure that my unique pointer is not copyable. I should not be able to say something like UNPTR employee Q is equal to P. To make sure that two different things, I cannot copy another one. So that takes care of being uniquely pointing. Okay? Make them both deleted. So neither they can be copied nor set to another one. So this is going to be, this is taken care of. Very easy and straightforward. But there should be no problem moving one, because if you move a unique pointer to another one, you still uniquely are pointing to something, and you remove the data of the old one. So moving the piece, so if I actually move the P into Q, I should be okay. For that, copying it is very straightforward and simple. So I simply say, hey, if I am move constructing a unique pointer, what I would do, I simply say that my pointer will point to the pointer of the other one, and I'll remove the other one. Therefore, still unique. I can pass the data from one unique pointer to the other unique pointer. Still, I have only one thing pointing at it, not two. For move assignment, it's exactly the same. We have done this so many times. We know exactly how it's done. I'm going to say, okay, if somebody wants to move a memory to mine, I cannot move to anything else anymore, point to anything else anymore. So if I am not the same, delete my stuff, my employee, now take over of the other employee and return this. Therefore, moving is perfectly okay. The fact that unique pointer's job is to only point to one object and no one is allowed to point to that object is accomplished by this. Now, I want to be able to say, hey, now that you created that, I want that P to act like a pointer. So I want to be able to say, see out target of P and L. Print that employee up. It's a pointer, right? This is supposed to be a pointer. P is supposed to be a unique pointer pointing to an employee. So I want to do target of P to print that out. So target of P is essentially, target of P essentially over here is supposed to be the reference of this dynamic employee, correct? That's OOP345 code. I don't need to do anything extraordinary over there. All I need to do is to say, if the unary operator asterisk was used, where is it? Unary operator asterisk operator was used, return the target of the pointer, which is a reference of a type. Done. So target of is working now. Okay? Not only that, what if I wanted to access the salary in there? Because we know that pointers are supposed to be able to go inside something, and so I need to be able to go inside and take care of the salary, right? So if something like this is used, that P should be the address of the employee, right? And for that, again, I can easily overload the arrow operator saying, hey, if arrow operator is coming out, return a type pointer, and top pointer is the MPTR, whatever that's in there. So that is taken care of too. What if somebody wants to actually know what is the exact address? What if they actually want to see where this thing is sitting in memory? They need to know the location. For that, I simply say const void pointer get const, and in here I'm going to say return MPTR. So if somebody wants to know where the thing is sitting at, now they can. I can actually say cout employee object is at p.get. So that pointer actually gives the address. I could have casted the thing. So initially I have done this. Okay, so I overloaded casting to void pointer. I'll remove that one. I'll tell you what. I'm not going to use that over here. Anyways, so down to this point, everything is good. Apart from, still I have to delete the damn thing when I'm done. And for that, again, I have a very easy solution, which is essentially a destructor. Because now this template is a class, all I need to do is to say, hey, when the unique pointer is outgoing out of thing, delete it. So now my unique pointer has a employee over there that is dynamic, and when it's done, automatically deletes itself. So I don't need to worry about anything being deleted anymore. I just create a unique pointer for my dynamic memory, and when the program's running, hopefully if I don't have an error here, when my program's running, okay, oh, sorry, wrong thing. Wrong button. Yeah. So a new employee is created, and as soon as it's created, it obviously an employee is instantiated, and after it's instantiated, it goes to the constructor of unique pointer, and the address in which it's instantiated is kept inside the unique pointer, and it's done. So now my pointer over here has an MPTR that is actually the employee. So that is good. Then the next thing, I'm going to say print the target of P. So that goes to the overload, returns the target of P as a reference. Therefore, it's a reference, and it's going to print the employee. And if I want to access the salary inside, I'm going to say P arrow. Now it returns the address, and then the salary is printed. And I can even see where the employee is sitting at. And as soon as the program is done, my unique pointer deletes the employee, and no memory leak is going to happen. Okay? Now, this unique employee is already implemented. It is in memory. My attempt of simulating it was to just, yes. Pardon me? Fixed?
I think it was just Denise.
Oh, no, it's the rest of them. I'm sorry, it was a big. So Yeah. So what I'm saying over here is that um, I could change the code of this one. I'll show it to you later with unique pointers. So essentially, in here, I could just remove this. So let me actually show it to you. So this PRGCPP, I'm gonna call it LFA. I'm gonna call it HUNPTR tester, and see what I'm gonna do. I'm gonna come in here. In here, I'm gonna say memory, and in here, I'm gonna say unique pointer employee. Exactly the same. No difference. So, but the difference is over here, you gotta be careful. What they did is much better than mine. I was just barely trying to explain to you how unique pointers work. It's nowhere close to it. They have done it much better than me. Okay. So that's that one. So this is essentially, and we don't need Seneca anymore. Okay. Now, the tough one, and I'm going to bring the code up for you and explain, is a shared pointer. Now, what is a shared pointer? New item. That's going to be a little hard to grasp, but I'll try to explain as the best I can. Please go home and walk through it and see what it is. A shared pointer, so a unique pointer doesn't allow copy, which means one pointer at a time can point to a piece of memory and that's it. With a shared pointer says, what the shared pointer says is that we can all point to a same piece of memory, many of us. But we'll make sure that that piece of memory is not deleted until the last of us is gone. So a shared pointer essentially counts. As it's being copied, it adds to a counter to see how many pointers are created. And when it's getting deleted, it counts back. The problem is that immediately you would think, can I put a static counter in there and count how many? You can't, because static pointer is shared between all of the classes. I want a counter for each individual allocated memory. So if I have a unique pointer for an integer that I am actually, shared pointer that I'm creating for an integer, only those who are pointing to that integer will be counted, not another one. So I cannot use a static pointer, static variable to count. Instead, what I'm going to do is this. Please don't look at all the code as I'm explaining, then go through it. Okay, number one. Obviously, I need to pointer for a type, whatever type that I'm pointing. Number two, because I cannot have a shared counter for all the objects of this type, I have to create a shared pointer to a specific object that is created. Therefore, I'm going to create a dynamic integer counter and create a counter for every and each memory location that I am pointing to. And I only instantiate it when I have a newly piece of the new piece of memory allocated. So if that's the case, then deleting will be difficult. I cannot just delete. I have to count and see how many shared pointers are pointing to that piece of memory. So I will change the delete command to my own and I call it wipeout. I didn't know what to call it. delete. If I call it free is already used. I could have called that I don't know. I called it wipeout. So the wipeout function replaces delete. What does it do? It says if there is a counter, so you see this counter that is null originally, if there is a counter, reduce it by 1. That counts how many pointers are there. Then it says if there is a counter and what was reduced caused to become 0, it means I was the last one pointing. Therefore, delete my pointer and delete the counter, both of them. So this delete will be used instead of a regular delete. This delete checks, am I the last one? If I am, wipe everything out. If I'm not the last one, don't do anything, don't delete anything. It's just me that is going, and there are still others pointing to that piece of location. So this delete thing is going to take care of that. Now, let's come over here and start creating it. Number 1, when I am creating, let me just bring the tester up so you can see the tester. So this is the shared pointer thingy, okay? Let me collapse the thing there. So I'm creating a shared pointer of type employee, and I say P new employee, yada yada yada. Okay? So when this is happening, a new employee is going to be in that shared pointer P. So I'm going to come over here and walk through it and see what happens. A new employee is created, it comes over here, it sets the PTR to the employee that is there, then it checks. It says MPTR, so I'm initializing. Becomes a new because it's the constructor, it means it's a new piece of memory. Okay, it's a new thing that is getting created. Then it says set the counter to a new size t with the value of 1 if that PTR is actually pointing to an employee. If it's not pointing to an employee, it's just a shared pointer that is not pointing to anything, so the value will be 0. So it will have a counter, but it will be 0. Right? So you can create a shared pointer, either pointing to something or pointing to nothing. If you are pointing to something, obviously I'm the first because it's a constructor, 1 will be set, or you are starting with a null, which becomes a 0. It means I am there, but I'm not pointing to it. That's the constructor. When you are copying a shared pointer, now what happens over here? If I'm copying a shared pointer, I'm going to set the pointer, my pointer, to point to the same thing that the other one is pointing. And I'm going to make my counter to point to the counter of the other one. Then I'm going to say, if actually there is an employee, add 1 to the counter. So if I'm copying a pointer that doesn't point to anything, nothing's added to the pointer, they're all 0. But if it is, then I'm going to add 1 to the pointer. So when a copy is happening, it adds 1 to it. Now, the copy assignment is the one that the first time I'm using wipeout, which means now I have a shared pointer that already exists. And I have another shared pointer. I want to set one shared pointer to another. Like here, Q is equal to P. You see that? I'm setting one to another. So what does it do? It says, am I the other one? What's the usual thing? So if I'm not the same, then that's the assignment is supposed to happen. If it's not, wipe the data out. What wipeout does? If this shared pointer is pointing to already existing stuff, okay, and there are other pointers pointing, nothing will be deleted because the memory is being pointed for something else. But if the one that is being set is the last one pointing that piece of memory, wipeout will delete it. Remember, wipeout wipes out already existing data only if I am the last one. And then I'll do the shared one, and the resting happens like the other one. If it's not null, it includes. Moving is straightforward. There is nothing wrong with copying when you're moving. That's very simple. You're creating a new one and you're moving something from the other, so it's going to move everything and the other one becomes null. So moving is moving. Move construction. Move assignment is the one that you have to call wipeout, which means if I am actually assigning something to another and I'm moving the other one to me, I have to make sure to first wipe out anything that I'm pointing at. So again, goes to the same thing. Wipe out if I'm the last one, and then you move the rest. Count over here tells you how many of us is pointing to that piece of memory. You can actually detect that. MPTR over here does the same thing. You can get the type out. You can, so these two we already know. And this one I'm going to change it with get to. So this one's going to be const void pointer get const return. So I can see what I'm actually pointing at. And in my destructor, I don't do delete. I'm saying delete the stuff that I have if it's the last one. Therefore, many can point to the same place. Now, if you are looking at the tester that we have over here, what happens is that I will start it. So let's again go to the left. Okay. I'm going to the tester. The first one is getting created. It comes in here. The employee is created dynamically. Then it goes to the constructor over here. And because PTR is not null, what happens is that it's going to actually instantiate it. And this will point to an integer that holds 1 in it. Then it comes out. The second one is created. That one has, so I am creating another shared P2. This one's going to have 1, 2. So if I look at P2, you will see the counter of P2 is 1. So P2 has its own employee, P1 has its 1. Now I'm going to come over here. Now, oh, I bypassed it a little too quickly. Just a second. One more time. Now, if I go to the move, the constructor for the first one is an empty one. Therefore, the counter is 1. But the move constructor for the second one, it constructs an employee. Oh, that's the copy constructor too. Fine. Let it go. Then it comes out. Now I'm going to say Q is equal to P. So what happens essentially, it goes to the move. If we are not the same, first it's going to wipe out the information that I had, and then it's going to move the other one and add 1 to the counter. Therefore now Q is 2, which means Q and P are both pointing to the same place. Now it's going to print the value out. The employee, this one prints P and this one prints Q. But when I want to get out and these are dying, when it goes to first wipeout, the wipeout over here checks, makes sure the counter is 0. If the counter is 0, it deletes that one. That's P2 dying. Now it goes to the next constructor and it says wipeout. It comes over here. It sees that MPTR is not null. Therefore, it reduces it by 1. Now it's pointing to 1. Because it's not 0, it will not delete the first one. Now, Q will be deleted. Q, because it was pointing to the original one, the value became 1. Now, it's pointing to 1, it becomes 0. Because it's 0, it's the last one, and it deletes it. Therefore, no memory leak. So as you see, based on how many shared pointers are pointing to the same location? Only the last one will be deleted, and therefore there's no problem. So this is called the shared pointer, and these are all used for dynamic memory allocation. Okay, and again, shared pointer is exactly the same thing that you have. You can just change that one to shared pointer, and it's going to be the same. Now, so I'm going to call this S. So I'm going to give you some simple examples of the real one, and then we're going to be done. So let me open it up. So unique pointer basic example, just for you to see what it is. Again, you create a unique pointer, you put a value in it, and you use it exactly like a pointer and deletes at the end. So that's a unique pointer basic. It's a very simple and straightforward thing. Everything works exactly the same way like I wrote over there. For a shared pointer, take a look at make shared. You see that? So make shared safely creates and efficiently creates a shared pointer. So whenever you want to have a shared pointer, instead of writing shared pointer SP, write auto SP, make sure, and you put the type and you put the values you want for that one. So it dynamically allocates an integer and puts 25 in it. You can do the same thing with the employee, just put the arguments of the employee in there, where it works the exact same way. Okay, so essentially make shared efficiently creates a shared pointer for you. You can use it manually too, but that's a better way of using it. The one that I use over as count is actually called use count. So you call it use count and it shows how many shared pointers are pointing to it, and the rest is identical to it. You can use shared pointer exactly like the regular pointer. As you see, you pass the shared pointer to data. When it comes over here, when it's finished and the data wants to die, it will not delete it because the original one's still pointing to it. Therefore, it's very safe to use it in shared process with absolutely no problem. And that's essentially the shared pointer. Yeah. So unique pointers, only one pointer can point to a piece of memory. Shared pointers, many pointers can point to a piece of memory, and the last one standing will delete. Questions? Suggestions? Objections? We're good? Okay, what I want you to do, please go home, play with this thing, and make sure that, I don't know, use it around with dynamic memory allocation and see how it works. Change some of the old classes that you had that use dynamic memory allocation with smart pointers and see how they work. For the quiz, did I tell you what the quiz is going to be? Did I? I'll tell you one more time for people who are listening on a recording. You're going to receive a class. You're going to have a data file that holds binary records of the same class. Then I'm going to ask you to show me a record in the middle and modify it. Show me the last record, show me the first record, print everything backwards. And that's it. That's going to be your quiz. And you should be able to do that. Okay? I will post the detailed stuff of the quiz soon, so you'll see exactly the same thing we always have with the announcement. And the next day you're coming in, this quiz is going to be very short, like 20 minutes, because it's very standard. I just want to make sure that you can do the file access, random access. And then we're going to talk about parallel processing. So the next day you're coming in, we're going to dig into parallel processing, threads, atomic values, mutexes, and things like that to see how we can actually run one function, 5 processes at the same time. So 5 different instances of the same function. Questions? Any questions? No questions? All right. Have yourself a beautiful day, and I'll see you on Thursday. Bye, everyone.